Bismillahirrahmanirrahim. Assalamu alaikum. In this video, we will talk about the concept of regularization. When we discussed polynomial regression, we encountered the issue of overfitting. We analyzed overfitting in detail, and we discussed a couple of solutions which we can potentially employ to handle or to avoid overfitting. I can give you a quick recap what we discussed earlier before we move to the topic of this video, regularization. So what was overfitting? So the overfitting occurs when we make the model too complex such that the model is fitting to the data, but not the actual true function. And the solution we discussed was that you can avoid overfitting by splitting your data into two data sets. One data set is called training data set and the other is called validation data set. By carrying out train and validation split of the data, we can handle overfitting. Because you expect that overfitting would cause or would give you poor generalization performance on the testing or validation data. The other solution we discussed to handle overfitting was you take more data points. When you have more data points, the model of reasonable order would not fit to the data, but it would try to fit all the data points. And another solution which we can employ is the topic of this video, that is regularization. Let's talk about what do we mean by regularization, and let's understand this concept in the context of linear regression. Okay, I will first give you an overview of regularization in general. The concept is very broad, but we will see in the context of linear regression or polynomial regression. So this regularization encourages the model coefficients to be small by adding some function to the loss function. And that function is a function of your unknown coefficients or variables. So the idea is that we add a penalty term to the loss function, to the error, and this addition of penalty term encourages the model coefficients to be small during the minimization process. So we had this loss function in the least square problem. We're going to add a penalty term, which we call regularizer, in the loss function as this. So I had this loss function L of theta. So I had this loss function for example, this was a loss function in the least squares, and I have added this additional term R of theta, and I call it regularizer. I will also talk about what is lambda here. Right? So I have modified my loss function from L of theta to L of theta plus lambda times R of theta. This R of theta is my penalty term. And this modified loss function we refer to as that this is a regularized loss function. And this R of theta is a regularizer. Lambda is a parameter that maintains the trade-off between regularizer and the original loss function, because this lambda here is controlling the relative importance of the regularization term. Right? So it is maintaining a trade-off between L of theta and R of theta. Right? So this was a very quick overview of regularization in general. Now we're going to talk about different types of regularization in the context of least squares. The first one is L2 least squares regularization. It is also referred to as ridge regression in the literature. So what is the idea of regression? So what is the idea of regularization? We want to discourage the model coefficients from reaching large values, right? we can use a very simple regularizer, which is a square of norm of the coefficients. If you add this term to the regularized loss function, and when you find theta such that the loss function is minimized, you are also minimizing the square of the norm of theta, and this will encourage the model coefficients. In fact, this will discourage the model coefficient from reaching large values, right? Since this is square of the two norm of model coefficients, we call this term as L2 or a small L2 penalty. And since we are using this regularizer, we call it, this type of regularization is called L2 least square regularization, right? So when we choose this L2 penalty, we have this loss function. So this is when we don't have regularizer, and we have added lambda by 2, in fact lambda times r of theta. My r of theta here is Euclidean square of Euclidean norm of model coefficients. So as I said earlier, so this maintains a trade-off between fit of the model to the data, because the first term is finding thetas such that your parameters or your model is fitting to the data, and the second term is the square of norm of the coefficients. So lambda is maintaining a relative trade-off between these two quantities. If model is fitted poorly, you expect the first term is large, and if the coefficients have high values, you expect the second term, the penalty term, is large. And obviously, if you choose a large lambda, it is going to penalize coefficient values more. If you forget this mathematical formulation, the intuitive interpretation of regression or of regularization is that we want to minimize the loss function, but at the same time, we want to minimize the norm of the coefficients as well, right? Because we have introduced the norm of the model coefficients in the minimization function, in our objective function that we want to minimize, right? So intuitive interpretation is we want to minimize the loss function, we want to minimize the error while keeping the norm of the coefficients bounded, or while minimizing the norm of the coefficients at the same time. Okay. So if you see this modified loss function, this is still quadratic, right? In fact, this is still convex. Every quadratic function is a convex function. Sorry, not every quadratic function is a convex function, but here this is a convex function, this is a quadratic function. That means we can also obtain the solution of this minimization problem analytically in the same way when we derive the solution for linear regression, right? Okay, so regularized loss function is quadratic, and we can find a closed form solution. If you take derivative of this regularized loss function with respect to theta, you take a gradient, and this is what you get. For the first term, you get, because you can write this as y minus x theta transpose into y minus x theta half plus lambda by 2 theta transpose theta, right? And when you take gradient of this with respect to theta, these two terms what we obtained earlier, but due to regularized penalty term regularizer, we get this additional 2 lambda theta. And when you substitute this equal to 0, we can move x transpose y to the right, and we have x transpose x theta plus lambda theta. And when you take theta common, you get x transpose x plus lambda I, and this implies we have theta is equal to x transpose x plus lambda I whole inverse x transpose y, right? So this is a closed form solution for a regularized, in fact, L2 least square regularization, or for ridge regression, right? Okay, if I make lambda is equal to 0 here, what did you get? A non-regularized solution, right? When lambda is equal to 0 means you have not taken into account a penalty term. So we have a non-regularized solution. If we see the other extreme, when we make lambda is equal to infinity, the solution is a zero vector, right? Because this, when you take inverse, this will move your theta to be 0. But your solution is, if you note here, the solution is a function of lambda. And we need to know the value of lambda. And we learn the value of lambda by, again, using validation data. So lambda here is a hyperparameter. We can learn the optimal value of lambda during a validation, or by evaluating loss on the validation data. Okay, let's take one example. If we take too small lambda, that is, we're not carrying out any regularization, and we take very large value of lambda, we're not giving any weightage to the data. We're only minimizing a penalty term, right? Because if you take lambda very large, you're giving more weightage to the penalty term. Or we can say that for large lambda, we're not giving any weightage to the data. So in practice, we use very, very small values of lambda. In fact, that is almost close to 0. But even a very small value gives us very, very good performance, or gives us allows us to handle overfitting. Right? So since we use a very small value of lambda, instead of using lambda, we work with natural log of lambda, right? And obviously, if you know log of lambda, you can recover lambda from log of lambda by raising exponent to the natural log of lambda. Okay, so let me give you an idea how regularization work, or what are the benefits. How can we avoid overfitting on the same problem when we discussed polynomial regression. So if you recall, we chose a function sine 2 pi x. This is my original function, and we took 10 data points, and we tried to fit a polynomial of order 9. When the polynomial is order 9, we had 10 coefficients, which we want to learn using linear regression. And when you learn those 10 coefficients, because you only have 10 data points, so the model is exactly fitting to the data, but not the actual true function. Right? When log of lambda is minus infinity, what is the value of lambda? 0. Or we can say we have not introduced any regularization. By taking a very small value of lambda, say lambda, when natural log of lambda is minus 18. See, we are still fitting a 9th degree polynomial, but by introducing a very, very small regularization, we have avoided overfitting. But if you add too much, if you use a very large value of lambda, say when natural log of lambda is equal to 0, so lambda is 1. So we have a too much regularization here. Right? Again, so the model is underfitting, or we are too much. In fact, we are not fitting the model to the data, because when lambda is equal to 1, you are giving too much weightage to the penalty term, or you're not giving any weightage, or you're giving less weightage to the data. Right? Okay, so what's happening here? If you remember, when we obtained the coefficients for a model, when we had overfitting, we had very large values of coefficients. But let's see what is the effect of this regularization on the values of the model coefficients. Okay. So when we had no regularization, right? You see, so in all the cases, we're using m is equal to 9. So we're fitting a 9th degree polynomial. That means we are finding 10 coefficients, but in the absence of regularization, we're getting very, very large values of these coefficients. Right? So by introducing a very small value of lambda, which is in fact x to the power minus 18. See, it's a very small value. But by introducing this small value, we can obtain, so we have discouraged the model coefficients from growing large. And obviously, when you have too much regularization, most of the model coefficients would be 0, because you are not giving any weightage to the data. As I said earlier, lambda is a hyperparameter of the model, and we learn it in practice using the validation data. If I ask you to find the value of lambda, say for this particular example, and you separate your data into test and validation data, this is the value of error of the loss function on validation data and test data for different values of lambda. If you see on testing data, right? So the error is going down and eventually increasing, right? But for validation data, so the error grows, right? So error grows, but it stays constant. So here, no regularization. Here, too much regularization, right? So this is the regime over which you can say you can choose any value of lambda in this range. Let's try to understand ridge regression using graphical visualization in two-dimensional space. We assume that we have two coefficients, θ1 and θ2, and we have a regularized loss function in which the first term is the least squared loss function, and the second term is the penalty term. So by choosing good value of lambda, we can avoid overfitting. And when we minimize this regularized loss function, we have seen earlier that irrelevant features get small but non-zero value in the regularized solution. So at this stage, you know why do you get small, but you don't know why do you get non-zero. But let me explain this with the help of graphical visualization. So for example, we take these contour plots for the loss function, least square loss function, and so these red contours are for the penalty term. Contour plots shows the area at which the function have the fixed values, right? For example, if you take this inner red contour, So for every point on this contour, equilibrium norm is same. Similarly, if you take a point on the outer contour, let's say this contour, so every point on the outer contour would have the same value of the equilibrium norm, right? So we have the contours for the least square loss function. We have red contours for the penalty term, including lambda. And we want to minimize the sum of these two functions, right? So where is the minimum of the least square loss function, right? So this blue dot in the center, right? So this is the point where the least square loss function is minimized. When lambda is equal to 0, no regularization. So, and when you solve this minimization problem, you get this blue point, which is in the center of these blue contours. Okay, but now we have a penalty term. So where is the minimum of the penalty term? Origin, right? When you take origin, theta 1 is equal to 0, theta 2 is equal to 0, equilibrium norm is 0. This is the minimum you can have the value for the norm, right? So you want to minimize sum of these two. So blue contour state that you have to be as close as possible to the center, the blue dot center. Penalty term enforces that penalty term requires us that we should be as close as possible to the origin, right? So the minimum of sum of these two functions is achieved when two contour plots meet each other, right? And so this is your optimal theta, or theta for which the regularized least square function is minimized. If you increase the value of lambda, if you choose a larger penalty, you get more narrow blue contours. And then the contour plots meet each other. These two contour plots meet each other at a point closer to 0 because you're giving more weightage to the penalty term. For larger lambda, you expect this point to move towards origin. And for smaller value of lambda, for smaller regularization, you expect this point to move towards a non-penalized solution. And recall, this blue dot is a non-penalized solution. Okay, I hope this is clear now. But what's the issue here? The issue here is irrelevant features get small but non-zero value because the intersection of these two, there's very less probability that intersection would be at these corners where one of the coefficient is 0, or this corner where theta 1 has some value but theta 2 is 0. Okay. We talk about solution of this. Ideally, we would like to assign 0 weight to the irrelevant features. And this is achieved by another type of regularization, what we call L1 regularization. And this is also referred to in the literature as Lasso regularization. So in Lasso regression, in L1 least square regularization, we use L1 penalty instead of L2 penalty. L1 penalty means instead of using equilibrium norm in the penalty term, we use Manhattan norm or we use one norm. So we use this regularizer. So R of theta is one norm of and the model coefficients. So if we take this regularized function, we get this regularized loss function. And this is also referred to as least absolute shrinkage and selection operator Lasso. And that's why we call L1 least square regularization as Lasso regression. Okay, if I ask you to have a similar graphical visualization of Lasso regression, what we had for a ridge regression. Right? So blue contours won't change, but those red contours in ridge regression would be replaced by sorry. So these contours. So these are these diamond shape. Right? So this is each of these contour represent. So every point on this outer contour would have the same equality norm. Sorry, they would have the same one norm, Manhattan norm, because this is simply theta 1 plus theta 2 is equal to, say, some constant value, call it C. And when you plot this for some value of C, you get these red contours. What's the difference here? Right? An interesting thing that greatly explains the difference between ridge regression and lasso regression is that in the case of lasso regression, these two contour plots will meet each other with a very high probability that these two contour plots would meet each other at these corners. And what are the benefits? If you see at this corner, at any of these corners, so one coefficient has some value, but the other coefficient is 0. Right? So that's why we say that lasso regression gives us a sparse solution. It makes some of the parameters exactly 0. In ridge regression, we get irrelevant features get smaller value, get smaller weights, but they're non-zero. Why? Because it is almost never the case that you get intersection of the contours at the corner points in ridge regression. But in lasso regression, we always get the corners, we always get the intersection at the corners of the diamond. And therefore, we say lasso regression gives us smart solution. Okay. So we have an area in signal processing, what we call compressive sensing or compressive sampling, in which we are always after sparse solutions. And this has been an active area for in the last 2 decades. Thousands of papers have been written around lasso regression or exploiting sparse solutions in the last 20 years. So, so now you know lasso regression, you know ridge regression. Right. Okay, let's talk about another type of regression, which is a combination of ridge and lasso. And that is what we call elastic net regression. In ridge regression, we have error plus lambda times square of iridian norm. In lasso, we have a penalty term which is which is one norm or Manhattan norm, sum of absolute values of the coefficients. So lasso optimization is computation expensive than the ridge regression. Because in ridge regression, you have a very nice, elegant quadratic function, and which you can minimize. That's differentiable, and you can minimize either using gradient descent or using analytical approach. Right. Due to the corners included in the solution in Lasso regression, a regularized solution will have some weights equal to 0. But there's a problem. Obviously, the solution would be sparse in general, but that is going to introduce bias into the solution. So there's a possibility that the actual coefficients are not 0, but you are enforcing them to be 0 in Lasso regression. Right? So we have pros and cons of ridge and Lasso, right? And we can define a regularization, what we call elastic net regression, in which we take into account both L1 and L2 penalties. So in elastic net regression, we minimize this regularized loss function. Again, the first is the least square loss function. The second term is L1 penalty, and the third term is the L2 penalty. And obviously you can see that ridge and Lasso are special cases of elastic net regression, and linear regression with no regularization is also a special case of elastic net regularization. So this elastic net regression, it combines the strength of both Lasso and ridge, but obviously it would require to find hyperparameters lambda 1, lambda 2. And again, we can find lambda 1, lambda 2 by carrying out train and validation split of the data. So this was an overview of regularization. We have seen regularization in the context of linear regression. We've talked about ridge regression, Lasso regression, and finally, very briefly, elastic net regression. Okay, so we stop here and we'll continue in the next module. Thank you, Ji.